Okay, so as we start the next section, we're going to continue talking about finding the zeros for polynomial functions. So remember that finding the zeros is the same thing as finding the x-intercepts. All right, so we're going to start with this example. Now, what I want to do as we get started is I want to remind you of what the examples that we have looked at in the last section looked like. Okay, so I'm just going to kind of come up with something over here just as an example. So an example from the previous section might have looked like this, where we were asked to find the zeros. All right, and so we talked about how we would put a 0 in for the y because we were looking for the x-intercepts. And then once we did that, we would factor what we have on the right-hand side. And note that what we have, the x squared minus x minus 12, is a quadratic, so it's fairly easy to factor. So we would have x and x for the x squared. For the 12, we would have a 4 and a 3, and then the 4 would need to be negative, the 3 would need to be positive, so we would get that quadratic equation factored, and then we would set each of those terms equal to 0 and solve. So we would have x is equal to 4 and x is equal to negative 3, and those would be our zeros. So what I want you to think about as we move into this next section is the step that goes from the second line to the third line. So if I take this expression that they give me in this example, 2x cubed plus 11x squared minus 7x minus 6, and I set it equal to 0, and then I try to factor it, I'm going to get stuck. Okay, so this one is not something that I have a skill to use in factoring. It has 4 terms instead of 3, so it's not going to factor into that double set of parentheses like we have over here. Typically, we would factor by grouping if we have something that has 4 terms, but even that you could try and it's not going to work. Okay, and so we can do the second step. We can set it equal to 0, but we have a hard time on this problem moving to the third step because we can't factor it. So we need to look at some other options. How do we handle these problems when we are unable to factor the polynomial that we're given? And so that's what we want to talk about in this section, are problems of that nature. So they're going to give me this theorem that we're going to talk about in this section. The theorem is called the rational zero theorem. Okay, and we're not going to write the theorem down. We're going to just sort of work with the theorem on this example that we have right here. All right, so what the rational zero theorem says for you to do is you're going to take your polynomial function and you are going to label the very last term, so the term that doesn't have an x at all, you're going to label that the p. And then you're going to take the coefficient of the first term, the highest power of x, and you're going to label this the q. So this is what the rational zero theorem says to do. It says you take that last term that doesn't have a variable on it at all, and you assign the letter p to equal that value. And then the theorem says you look at your term that has the highest power and the number in front of that term. You're going to assign to be the q value. Okay? And then the theorem says that you are going to go in and you're going to write down all possible combinations of numbers that would multiply together to give you the p, and all possible combinations of numbers that would multiply together to give you the Q. All right, so I'm going to do the -6 first. Okay, so I'm going to think of ways that I can multiply two numbers, and I want to stick with whole numbers. I don't want to get into fractions. Two numbers multiplying together to make -6. So I could do 3 and -2. I could do 1 times -6. I could also switch the negative around. I could do -3 times +2. I could do -1 times +6. Okay, and so those are all the different ways using whole numbers that I can multiply numbers together to make -6. So now I'm going to kind of summarize my list a little bit. All right, so I have a +1 and a -1. So I'm going to come over here and I'm just going to write it plus or minus 1. I'm going to put those two together as an option, plus or minus 1. Okay, I also have that for the 2's. I have a -2 and a +2. So what I'm doing is kind of combining numbers where I can, and I'm also putting them in order. All right, -3, +3, and positive and -6. Now I'm going to do the same thing for the Q value. All right, so how can I make a +2? I can multiply 1 times 2, or I can multiply -1 times -2. So again, I have both the positive and the -1, and I have the positive and the -2. All right, so we're still doing rational zero theorem, still kind of talking through what this is going to look like. All right, so the next thing the theorem says to do after we've done this is it says to make fractions. So to put all possible combinations of P over Q. Now, I want to be careful here that I don't miss something by mistake. So what I'm going to do is I'm going to take all of these P values and I'm going to put them all over 1. All right, and I'm going to kind of simplify as I go. So I'm taking a P value and putting it over 1. 1 over 1 is still going to stay 1. This 2 over 1 simplifies to 2. 3 over 1 simplifies to 3. 6 over 1 simplifies to 6. Okay, so once I take all of those numbers and I put them over 1, I'm then going to take all of those numbers and put them over 2. So I have 1 over 2, which is going to be 1/2. I have 2 over 2, which is 1, and I already have 1 in my list, so I'm not going to repeat anything. The next one is 3 over 2, so that would be 3/2. The last one is 6 over 2. 6 over 2 is going to reduce to 3, and I already have that in my list. All right, so what I have done now is I have created a list of all, this is what the theorem says, this is the list that we've created, is going to have all the possible rational zeros for the function. All right, so what the theorem basically says is that if you have, and we're not going to get real hung up right now on the word rational, but what the theorem says is that if you have a zero, a rational zero, it is one of these numbers. All right, so I'm just going to say it is in the list. All right, so think about what we just did. We basically took this polynomial function where we had no idea what the zeros were. So it could be any possible number in the whole number system, so millions of different numbers. And we've now broken it down and we've said, okay, if there's a rational zero, it is one of these 12 numbers in my list. All right, and I'm saying 12 because we've got plus or minus 1, plus or minus 2, plus or minus 3. So the positives and the negatives. So we've narrowed it down from every possible number to a list of 12 numbers. Okay, so now the next thing I have to do is I have to figure out which of those 12 numbers are actually zeros for the function. So we know that this function has how many zeros? So we have talked about how the number of zeros in the function is equal to the degree. All right, so I know that the degree is 3. That's the highest exponent, so I'm expecting 3 zeros. All right, so now I've got my 12 numbers. I need to figure out which of the 3 are actually zeros of the function. Now, the easiest way to do this is to take one of the numbers in the list, okay, and plug it into the function. So I'm going to just pick one of the numbers. I'm going to pick 2. All right, so I'm going to come down here somewhere on my scratch work, and I'm going to say, all right, so let's suppose that x is equal to 2. It's one of the numbers in the list, okay? To check it, I'm going to put it into my function. So I'm going to go back to my polynomial function, and everywhere there's an x, I'm going to put a 2. All right, and then I'm going to go to my calculator with it, and I'm going to calculate what that's equal to. Now, I realize this is a little tedious. We're going to learn better ways to do it, but for right now, we're going to look at this and we're going to say, okay, the calculator gives me 40. So I know that this is not a 0 for the function. 2 is not. And I know that because when I plugged 2 into the function, I didn't get 0 out. Remember, if you're talking about x-intercepts, when you plug the x value in, the y value should be 0. So if the y value is 40, I know that I'm not looking at a 0. All right, so I'm eliminating that. That's not correct. All right, so let's try another one. Let's try 1. All right, so I'm going to do the same thing. I'm going to take my function. I'm going to plug a 1 in for the x. And put that in my calculator, and that time I do get 0. Okay, so this is a 0. So I did a good thing here in checking the 1 because that is a 0 for the function. Okay, so once we find a 0, then what we're going to do is we're going to, especially for a third degree polynomial, okay, so a polynomial that has an x to the third as the highest power, if I can find 1 0, then I can go ahead from there and use synthetic division to help me find the other ones. All right, so I'm going to write this down up here so I don't forget which one I used. Okay, so I'm making a list of zeros. I know that x is equal to 1 is one of those zeros. All right, so let me make a little room here. All right, so what we're going to do is we're going to do synthetic division with 1. Okay, so we know that that's a 0. All right, and remember you're going to put the numbers of the polynomial underneath. So we have 2, 11, -7, and -6. All right, and we're going to drop the 2 down. All right, from the last section, you should know how to do this. Remember, it's 1 times 2 is 2, and we'll add. 1 times 13 is 13, and we'll add. 1 times 6 is 6, and we'll add. Now again, you should expect to see that 0 popping up as the remainder. We've already proven that because we plugged the 1 in and we got 0. So we know that that should happen. That tells us that it's a 0. That just kind of confirms what we did when we worked it out down here. Okay? All right, so let's look at what we have left. So now I'm going to put the x's back into the bottom part. So remember that when you divide into x to the third, that your answer becomes an x squared. So we have 2x squared plus 13x plus 6. Now, note that what you have is a quadratic, and quadratics are things that we can hopefully factor and work out the rest of the way. So I'm going to take that expression and I'm going to see if I can get it factored. All right, so I know it's going to have to be a 2x and an x to make a 2x squared. For the 6, I'm going to try, let's see, let's do a 1 and a 6. All right, so I'm checking my middle terms. That's going to give me a 12x on the outside and a 1x on the inside, which will make the 13 that I want. So I'm going to go ahead and put a plus on both of those. All right, and then let's take each of those terms, just like we've done in the last section. Let's set them equal to 0 and solve. So 2x plus 1 is equal to 0. I'm going to subtract the 1 from both sides. Then I'm going to divide both sides by 2. All right, so I have another 0 at negative 1/2. And then my other term, x minus 6, or I'm sorry, x plus 6 is equal to 0. We'll subtract 6 from both sides, we'll get negative 6. And so that's going to be my third 0. All right, so that is part of what they asked me to do. They asked me to find all of the zeros for the function. All right, and then the last thing we need to do is factor it completely. Okay, so this is pretty much done for me. I can come back down here and get 2 of the factors. So I have 2x plus 1. I have x plus 6. And then the third factor is going to line up with the 0 of the 1. Okay, so we've done the one that gave me 1/2, negative 1/2. I've done the one that gave me negative 6. I just need the one that gives me 1. So remember that that factor should have an opposite number. So if the 0 is positive 1, the factor should be minus 1. All right, and so now we have the polynomial completely factored. So this is kind of a process that the first time through it seems like there's a lot going on, and the more that you practice it, the better you get with the steps and the quicker it gets. So I'm going to go ahead and close this one out right here, but then I'm going to come back and work a couple of other examples for you just so you can see a few more problems worked out.